So today let's continue on the node architecture study. Let's complete node architecture today. So last class we learned basic architecture for a wireless sensor node, right? So we can have different architectures. Basically, three kinds of architectures, right? And also we uh, have um, have learned different you know uh, you know processor system, right? For wireless sensor nodes, right? We can have the microcontroller. We can have DSP, we can have FPGA, we can have ISIC, right? As the sensor system, right? A processor system, right? Yeah, for the wireless sensor networks, right? Okay, and among those, processor systems, microcontroller is the most widely used one. Yeah, microcontroller. And today, let's continue to learn the communication subsystem. So here, instead of talking the whole system, we just talk about the communication interfaces. Yeah, because later, actually, we will spend more time talking about communication. So integrated with networking, right? So we will learn the communication and networking knowledge for different layers, such as the physical layer, the network layer, the MAC layer, medium access layer. Yeah, from that point of view to explore the communication subsystem. Yeah. So for the communication interfaces within a wireless sensor node, uh, so it's very important, very important. Yeah, we need some kind of fast and energy efficient data transformation, between wireless sensor nodes, right? Yeah, because uh, as we mentioned in our first class, right? So energy consumption is a restriction for wireless sensor node, right? Because we cannot, usually it's not that convenient to provide enough power, right? So enough energy. Yeah, so that's a big concern for wireless sensor node. Yeah. So here we try to find some energy efficient data transformation, way to, realize, communication among the subsystems within a sensor node. Yeah. And if it's faster, then of course that is better, right? Yeah. However, the reality is that because of the size limitation, because of the power supply limitation, you know, we cannot develop a very sensitive node with very fast, communication interface. It's hard to use parallel communication. Yeah, because parallel communication requires, a larger size. Yeah. So basically, we use the serial transformation here. Yeah, serial transformation for the, you know, communications among subsystems for wireless sensor node. Uh, so for the serial communications, we have a couple for interfaces, serial communication interfaces. One is the SPI. serial peripheral interface. So this one you may hear of, right? Yeah, serial peripheral interface. Another is GPIO, right? General purpose input output. So this GPIO I think is mentioned a lot. Not only for wireless sensor node, right? Sometimes for any kind of embedded system application, right? So this term GPIO is used a lot. Yeah. SDIO, right? Secure data input output. Yeah. So this actually this is not that widely used, right? Yeah. So this SDIO is not that widely used. I2C. Yeah. This is very popular. Inter-integrated circuit. Yeah. So this I2C is quite often used, within the wireless sensor node, among the processor and with other subsystems. Yeah. I2C is also very important. The same as SPI, for wireless sensor node. Yeah. And here, actually, sometimes we may also, use another serial communication interface, which is UART. UART, yeah. And it depends on what kind of wireless sensor node it is. Yeah, wireless sensor node it is. So later, if we have some time left, I can talk about UART for a little bit. So this is universal asynchronous receiver transmitter. Yeah. Okay, UART. It's also a serial communication interface, and also is a serial communication protocol. Yeah. And among these serial communication interfaces, the most widely used ones are SPI and I2C. SPI and I2C. Now let's see SPI. Yeah. So SPI, as I mentioned, is a serial communication interface, right? So it's a high-speed, full duplex synchronous serial bus. Yeah, serial communication interface. Yeah. So here it says high speed. Yeah. This is to compare with some other serial communication interfaces, right? So it's high speed. But if it's compared to parallel, communication means, right? So it's not that high speed. Yeah. And for this SPI, actually it doesn't have official standards. Yeah, doesn't have official standard. But the SPI interface should conform to the implementation specification of others. Yeah, yeah. So in order to get correct communication. Yeah. So when we implement, the communication with SPI, we have masters, we have slaves. So each of them should get consensus on the protocol, on the parameters, during this communication. Yeah. And in SPI interface, there are 4 pins. So MOSI. So this is master out, slave in. Yeah. So as I mentioned, there are master and slaves. Yeah. Yeah. So usually one master, either one slave or multiple slaves. And this pin is used to transmit data from master to the slave. Yeah. One device is configured as the master. Yeah. So it's easy to understand, right? Based on the name, right? Master out, which means the master device is transmitting data, right? It's sending data out. Yeah. And slave in, right? So it means it's coming, right? It's receiving data. Yeah. So the data is coming in. Another another pin is MISO. This is master in, slave out. Right? Yeah. So this is the opposite transmission direction compared with the first pin MOSI. Right? Yeah. Here, because for the master device is to receiving data. Right? The data is coming in to the master. And the slave device is sending data out, right? It's transmitting data. And in order to let the master and slave, they work synchronously, right? Yeah, so we need a clock signal. So this pin for the clock signal is SCLK. Yeah, this is the serial clock. Yeah. And by the master to send the clock signal that is needed to synchronize transmission. Yeah, that is to ensure the master and the slave, they are synchronous. By the slave to read this signal synchronized transmission. And the last pin is CS. Yeah. So it's chip select. Yeah, chip select. So this pin is used to communicate via the CS port. CS port. Some characteristics of SPI, serial communication interface. So both the master and slaves hold a shift register. Yeah, both of them hold a shift register. Think about how can they transmit data, with the serial mode, right? Yeah, so they use shift register. So every time shift out 1 bit, right? Yeah. So with time going on, right? So bit by bit, so it's in the serial mode. It's not like the parallel mode, right? So at one moment they can output multiple bits at the same time, right? Yeah. So using the shift register to implement this serial communication, serial transmission. So every device in every transmission must read and send data. Yeah. So the slave, the master, all of them should read and send data. So SPI supports this synchronous communication. Yeah, it's synchronous communication. Both master and slaves must agree on timing, right? So we use that serial clock signal to ensure this. Yeah, and they should also get consent with some other parameters during the communication. The first one is that the clock polarity. So this signal defines whether a clock is used as high or low active. Yeah, clock polarity, and also clock phase. Determines the times when the data in the registers is allowed to change and when the written data can be read. Yeah. So this is clock phase. Yeah. So both of them they should get consent with these two parameters. Let's see the table, with these two parameters, CPOL, right? Yeah, and CPHA, right? So this CPOL is the clock polarity, right? Clock polarity, that is clock phase. And based on the values of these two parameters, we may have 4 modes for SPI, right? 4 modes. The first mode is that when this clock polarity is 0, right? It's active low. And when this clock phase is 0. And the explanation, this description is that this 0 clock signal is low active, right? Yeah, it's low active because here is 0 for the clock polarity is 0. Yeah, so it's low active. And the sampling is allowed on odd clock edges. Data changes on even clock edges. Yeah. So these are the descriptions for one this clock polarity is 0 and the clock phase is 0. Yeah. What if the clock polarity is 0 but the clock phase is 1? So it's still low active, right? Yeah, because it's 0. But for the sampling is allowed on even clock edge, okay? And the data changes on odd clock edge. Yeah, so you can see this sampling and data change, right, is dependent on the value of the clock phase, right? Another 2 modes, that is when the clock polarity is 1, right? And we know, okay, this 0 clock signal is high active. And with different values for the clock phase signal, right? So we can, determine the, whether it's an odd edge or even edge to do the sampling, right? And what is the edge for the data changes, right? Okay. So this should be easy to understand, right? So it's, because we have 2, signals here, right? And for each one, they may have 0 or 1, right? So, and then together, we may have 4 combinations, right? And they are the 4 modes for SPI, right? Yeah. And for the 0 clock signal, for the sampling data change, depend on the value of these 2 signals. And so here we have 2 architectures for serial communication interfaces. The first architecture is shown here. You can see in this architecture, we only have 1 master and 1 slave, right? And you can see how to connect the pins with these 2 units, right? Yeah. So you can see, the 0 clock pin connect to 0 clock pin, right? Yeah. And here, MOSI pin, right? MISO pin, and this selection pin, SS, right? Yeah. So it's easy for this architecture because just the 1-on-1, right? Yeah, no other options. Yeah, so just directly connect them together, connect the corresponding pins together. The other architecture is that you can see is more complicated. So for 1 master unit, we have multiple slave units, right? Yeah. So in this example, for 1 master unit, we have 3 slave units here, right? So actually, we can have more. slaves for this kind of architecture. We can have more. And you can see that for the connections, right? For slaves, you can see actually they share, the connection with the pins in master unit, right? As clock, right? Master out, slave in, master in, slave out. Yeah. So they have to share with these pins because only one master, right? Yeah, they share that. But we have, more pins to select, which slave to communicate at a certain moment, right? And so here you can see that we have more selection signals. That is to select, different slaves, right? So this is SS1 connects to slave 1, right? SS2 connects to slave 2. SS3 connects to slave 3. Okay, so that is the SPI, serial peripheral interface. Next one is the inter-integrated circuit, I2C. And here is the architecture. Yeah, and you can see that for this I2C, so usually we have one master, and then we have multiple slaves. Yeah. And you can see it's similar to SPI, right? So the slaves, you can see they share the buses, right? So here we have two buses for the I2C, SDA and SCL, yeah, because there is only one master, yeah. So the slaves, they have to share, the buses. Yeah. And let's see what are these two buses. Yeah. So this SCL is the serial clock bus, yeah. And this SDA is the serial data bus, yeah. So they share these two buses. Serial clock, serial data. One is clock signal, one is data. And for the I2C, every device type that uses I2C must have a unique address. Okay, unique address that will be used to communicate with the device. And for the addressing mode, actually we have two kinds of addressing modes. One mode is using 7 bits, yeah. So 7-bit address. So that is an old mode, yeah. So in earlier versions, so we use this 7-bit addressing mode. So because 7-bit is not enough or not efficient anymore, with the modern applications, right? Yeah. So and then later, we developed the new mode is using 10-bit. It's using 10-bit, so it's 10-bit addressing mode. Yeah. And the I2C is multi-master half duplex synchronous serial bus. Yeah. So it's also synchronous serial communication. So at this point, for this, from this point of view, it's the same as the SPI, right? It's synchronous serial communication interface. And since each master generates its own clock signal, communicating devices must synchronize their clock speeds. So it's the same as SPI, right? So for any kind of synchronous communication interfaces protocols, right? So they should have the same clock signal. Yeah. So either share the same clock from the from the processor, or one of them should generate a specific clock signal and use this clock signal to synchronize other connected units. A slower slave device could only detect this address on the SDA line, while a faster master device is sending data to a third device. Yeah. So this actually is to kind of explain why we need this, synchronization, right? Why we need this, clock signal to synchronize the speed, right? Because if they have different clock, right? They have different speeds, right? So this problem will occur. A slower slave device could, detect his address incorrect, right? One faster, master device is sending out data. So I2C requires arbitration between master devices wanting to send or receive data at the same time. So there's no fair arbitration algorithm. Rather, the master that holds the IDA line low for the longest time means the medium. So some other characteristics for I2C. So I2C enables a device to read data at a byte level. Okay, a byte level, yeah, for fast communication. This is a little bit different from SPI. Yeah. The aim of I2C is to minimize cost for connecting the device. So I2C defines two speed modes, fast mode. So a bit rate can be up to 400 kbps, yeah, kilobits per second. So the high-speed mode, the transmission rate can be up to 3.4 megabits per second. And these speed modes, they can be downloaded to be compatible to ensure communication with some older components. Yeah. And so this figure shows the two addressing modes for I2C. Yeah. And figure A actually shows the older mode for older versions. That is 7-bit addressing mode. Yeah, 7-bit addressing. And this figure B shows the 10-bit addressing mode. And let's see this 7-bit addressing mode. Yeah. So you can see that for the message, right? Yeah, for the data packet during transmission, right? So here you can see we have a star bit. Yeah, so this capital S represents the star bit. Yeah, star bit. And followed with this star bit, you can see that we have 7 bits here. 1, 2, 3, 4, 5, 6, 7, right? So okay, so these 7 bits actually are the address for slave. Yeah, the address for slave. And then next bit will be the read or write bit, and follow the will be the acknowledge bit. Yeah. And then will be the base for data. Yeah, for the base for data. The data for transmission. Yeah, for transmission. And followed another acknowledge bit to confirm the receiving of these bits of data, and then another piece of data, another 7 bit of data. Yeah. Okay. And after the acknowledge bit, there will be the last bit, that is the stop bit. And this is the 7-bit addressing mode. For 10-bit addressing mode, so here is different here. Yeah. So you can see that the first bit is still this star bit, right? Yeah, this star bit. Follow this star bit, you can see actually we have file bits, right? And for this file bits, actually you can see the values are fixed, right? So the values for this file bits 1, 1, 1, 1, 0, right? So the values are fixed. So actually here, these bits define some other characteristics for this addressing mode. Yeah. So here actually these are not the values for the address. Yeah. Actually here you can see here we have this you can see 2 bits, right? And the values are XX. So these values are unknown, right? Yeah. X here refers to unknown value. Yeah. So here we have 2 bits here, right? And you can see followed with that here we have 8 bits. Yeah. So these 2 bits plus these 8 bits, so together we have 10 bits, right? We have 10 bits, and actually is specified here, right? Yeah. So these 2 bits here plus these 8 bits, and we form this 10 bits address, right? And here is the MSB, here is the LSB, right? Yeah. So yeah, this is the 10-bit addressing mode. Different with the 7-bit, right? Yeah, it's more complicated here. Yeah. So for actually the addressing for I2C, so it's just to let you know the basic knowledge, basic idea. Yeah. It's not required to figure out every bit and for 7-bit addressing or 10-bit addressing mode. And actually there are some more bits associated with the addressing mode, but here it just didn't show that. Yeah, it didn't show that. Okay. And let's summarize and compare these two serial communication interfaces. Okay. And SPI, so 4 lines, enable full duplex transmission. but I square C, 2 lines, right? Yeah. So here SPI we have this ISO SI, right? MO SI, MI ISO, right? And we also have the zero clock signal. We also have this selection signal SS, right? But here for I2C, we just have this SDA and LCK, right? Zero data, zero clock signals, right? Yeah, just 2 lines. But compared with SPI, I2C is has lower cost. And for SPI, no addressing is required. But for I2C, we have this addressing, right? Addressing issue. Addressing enables multi-master mode. Yeah. SPI allows only one master. That is to avoid conflicts. But I2C allows multi-master. Hardware requirement support increases with an increasing number of connected devices. I2C hardware requirement is independent of the number of devices using the bus. It's different. So the master's clock is configured according to the slave speed, but speed adoption slows down the master. Slower devices may stretch the clock latency, but keeping other devices waiting. Yeah. So actually, this is something, more deeper, right? Yeah, something more deeper. So we don't need to get familiar with that. Yeah. Speed depends on the maximum speed of the slowed device. So this is too easy to understand, because in order to get every device to be synchronous, right? Yeah. So we have to adapt to the slowest device, right? Yeah. If your speed exceeds the maximum speed of the slowed device, and then that will be a problem, right, for the communication between any device with this one, right? Because that slowed device cannot support that high speed transmission or communication. And for the I2C, so there are 2 speed modes, right? And the high speed mode is limited to this 3.4 MHz. And registers. So okay, other differences are not important. Yeah. Okay, so that's SPI and I2C. So the most useful, most widely used serial communication interfaces for wireless sensor node. Yeah. Okay, now let's have a break, and let's get back in 5 minutes. Okay, let's continue. So the last part for this lecture will be some prototypes for the virus sensor node. So we have the summary for the computer interfaces. So you can read about this by yourselves. For the prototypes of virus sensor node, actually we have more than these three. Yeah. So here just the three examples. Yeah, three examples. The first prototype for the virus sensor node is called iMode. iMode sensor node. Yeah. So this iMode is a multi-purpose architecture. Yeah, multi-purpose architecture. So it consists of these subsystems. The power management, right? Yeah, this is usual. Processor subsystem, sensing subsystem, communication subsystem, interfacing subsystem. Yeah. So you can see the first four subsystems, they are usual, they are common, right? For any kind of wireless sensors, right? For the last one, the interfacing subsystem, yeah, this is kind of new right here, yeah. So this interfacing subsystem, enables the interfacing and connection with external devices, yeah. Because sometimes for certain applications, we may need to connect the sensor node to some other devices, yeah, and then we need some interfacing, parts, right? Interfacing component, on the sensor node. Yeah. So this is the function of this interfacing subsystem. So this figure shows the architecture of this iMode node. So you can see here we have this CPU core, right? And we also have a DSP chip here, right? So actually they are the processor subsystem, right? Yeah. And here you can see we have this chip for wireless communication, right? Here you can see this is 802.15.4 wireless communication protocol, right? This is if you remember, right, what is this protocol? This is ZigBee, right? Yeah, ZigBee. This is a communication subsystem. And here a unit, power management. Yeah. So this is the power management subsystem, right? And here you can see we have these IOs, right? So we can regard this as the interfacing subsystem. And here you can see the sensing subsystem is not drawn here, right? It's not drawn here. So actually there are multiple sensors on this iMode sensor node. And yeah, as I said, there are multiple sensors on this iMode sensor node. Yeah. And for this multiple sensor board contains this one 12-bit 4-channels ADC, one high-resolution temperature sensor, humidity sensor, one low-resolution temperature sensor, digital temperature sensor, and one light sensor. So usually for wireless sensor node, if there are some default sensors on a wireless sensor node, so usually the default sensors will be temperature sensor, light sensor, and humidity sensor. So usually it will be one or all of these three for the default sensors. So for this M mode node, I2C bus is chosen to connect low data rate sources. SPI is used to connect with high data rate sources. And here you can see, the connections between sensors and these serial communication interfaces, right? So here you can see the temperature sensor, the light sensor, ADC, connects to the processor with I2C, through I2C. So the humidity sensor and this temperature. So one is digital, low resolution digital temperature sensor. One is high resolution temperature sensor. And this one and the humidity sensor, accelerometer, that connected via SPI. The processor subsystem, there is a main processor. This a microprocessor. So this is a voltage, frequency. This is the dynamic voltage scaling, and it has sleep and deep sleep modes. And because of this, it has the low power operation. And also there's, as the architecture figure shows, there's a second processor. It's a coprocessor, right? Actually it's a DSP chip. So it can accelerate the multimedia processing. The second prototype is called XYZ node. So in this node, you can see we have this power supply, power management subsystem, communication subsystem, sensor subsystem, and we have a new subsystem, mobility subsystem. So this is the node architecture. So this part I create is the power subsystem part, right? Power part. Here is the communication subsystem. And here you can see we have, here we have different sensors, light sensor with thermometer sensor, right? Accelerometer, right? So here is the sensor subsystem. And then here you can see that we have geared motor here. So this is the mobility subsystem. Mobility. So using the motor, we can trigger some component like camera or like some other actuating components. And this is actually it's the processor subsystem. Processor subsystem. So I think here we need to add the processor subsystem, because this is necessary, the essential subsystem. So this processor subsystem is based on this ARM 7 TDMI, this core microcontroller. Yeah. So you can see for this XYZ node, right, the processor subsystem is based on a microcontroller. What about the iMode processor node? That is based on a microprocessor, right? And what are the differences between microprocessor and microcontroller? We covered last class, right? And this is the maximum frequency of this microcontroller. Two different modes, 32 bits, 16 bits, yeah. And the capacities of the memory, peripheral components, DM controller, 4 10-bit ADC, 0 ports, SPI, I2C, SIO, RS-232. So RS-232 is also a serial communication, interface or protocol, and also general purpose IOs. The communication subsystem connects to the processor subsystem through SPI interface. And this component CSE5420 is RF transceiver. RF transceiver. So one RF message has been successfully received. The SPI interface enables the radio to wake up a sleeping processor. And the processor subsystem controls the communication subsystem by either turning it off or putting it in a sleep mode. Yeah. So in many wireless sensor nodes, they have this function, which is to either turn off the communication subsystem or let the communication subsystem sleep. Because in this way we can save more energy. Yeah. So this is a common implementation with wireless sensor node. Yeah. Because it's very important to find a way to save more energy, right? Yeah. So the third wireless sensor node, this is the hot probe node architecture. Yeah. And this wireless node, is designed for specific application. That is to monitor the pig production. Yeah. So this is a very application specific wireless sensor node. Yeah. And the motivation is that to monitor the movements between soul and onset of estrus, yeah. And detect cough or limping to monitor illness. So this is the architecture for this wireless sensor node. And you can see here, right, we have the sensing subsystem, right? Yeah. The components here. We have here is the communication subsystem, right? And the processor subsystem here, you can see, is based on FPGA core, right? Yeah. So we learned the four kinds of processor system for various sensor nodes, right? Microcontroller, DSP, FPGA, and ASIC, right? And here for this example, this various sensor node using FPGA as the processor system, processor subsystem. So for this one, besides this FPGA core, it also has another microcontroller. So where is the microcontroller? Oh, here. We have also a microcontroller here. Yeah. So both of them compose the processor subsystem. So this microcontroller in this various sensor node performs less complex, less energy intensive tasks. And and actually the main functions are controlled by this FPGA core, by this FPGA core. And here for the serial communication interfaces, right? So we have I2C, that is for the sensing subsystem. Yeah. SPI for communication subsystem. JTAG for in-system programming and debugging. Yeah. So this JTAG, right? So if you have taken CSE 3100 or CSE 5210 courses, right? So with the RPG board, right? So you will use this JTAG interface, right? When you try to program and download the code to the RPG board, right? So we achieve that through this JTAG interface. So that is for programming and debugging. And the serial RS-232 interface is for the interaction with PC. Yeah, so with the PC through this serial port. Okay, so these are the three examples of prototypes about various sensor nodes. So let me try to find some images for you. So maybe the images for those prototypes of the various sensor node are more intuitive.